Okay, good morning, everyone. The schedule for today is we have 2 hours of lecture with me on dynamic analysis with Opensees, and then after the coffee break with Cristoforo De Martino, Professor De Martino, you will see how to run parametric analysis in Opensees, and then after the lunch break, we will continue with the other session. We have 2 sessions of the course. Let's start with dynamic analysis on Opensees. So where we are. Yesterday you saw how to create and run an Opensees model, okay? How to create an elastic model, a nonlinear model with 2 different approaches, and how to run static analysis. Static analysis that can be monotonic or cyclic, right? Today we are going to do a dynamic analysis in Opensees. In particular, it's super lagged. No, extremely lagged. I don't know what's going on. You can see the first slide, right? In Zoom. I can see the slide. The first. No, I have the second on my screen. I don't know what's going on. Okay. How we can solve it?
Yes. Maybe you can stop sharing and
share,
start
yeah.
again. We can have a chance.
Okay, let's start again. Nope. No. No, it's stuck. Okay.
Okay, maybe it's the
Let's start again.
internet.
Internet, I'm using
Maybe you
this
can
one.
have a different Wi-Fi.
I know Zoom also.
Yes.
Yeah, it's
You can search and different Wi-Fi.
disconnect. Yeah.
Okay. Oh yes. Maybe this one.
Yeah, it puts automatically. So
Yes.
Okay, let's try again.
Yes.
Okay, let's start. Okay, let's try if now. Sure, but it's a problem. No, that's not a problem. Okay. So the outline of today's lecture is how to run model analysis. I'll show you with a couple of new commands in Opensees, and then how to run time history analysis with some examples and exercises. And also you will have an exercise tonight for the live workshop on that, okay? So let's start with model analysis. What's going on? You know how to run static analysis, right? So you know how to compute the stiffness matrix, okay? You know how to compute stiffness matrix in both elastic and not linear cases, okay? What's model analysis? I'm not going inside in details in this part. I think everybody knows the theory behind. Model analysis is just you have this equation here with masses and stiffness, and you compute eigenvalue, eigenvector analysis. You perform eigenvalue and eigenvector analysis, in which the eigenvalues are the network frequencies of the structure. Okay, the eigenvector are the modal shapes. Okay, so you can do a decomposition of the structure in the behavior of the structure in the modal world. Okay, how to do this in Opensees? What we need? We need something for creating and assign masses. Okay, we need. I'll show you very briefly how to define element loads. You only see before you only saw how to declare node loads, okay? And then how to perform eigenvalue eigenvector analysis and how to take the results, okay? First of all, yesterday Cristoforo told you that in Opensees you have to be consistent, okay, with the system of unit system. Be careful, since we are passing from geometrical and flowed world, we are passing through masses, okay? So be careful to the, I don't know what's going on in the chat. Okay. You have to be careful with the system, the unit system, okay? So if your system, you're defining a system in millimeters second and so on, you have to use as gravitational acceleration 9800 millimeter over square seconds. Otherwise, you have to use 9.8, okay? So be careful also to this part here, okay? How to declare masses? You can use two different approaches, okay? You can use lambda masses, okay? Like this. So you can declare, when you declare the nodes, you declare the tag of the nodes, the coordinate, and then you can declare the masses. You need here a quote unquote dash mass before this value here, okay? Otherwise, you declare the masses, the nodes, and then you assign to that node the mass that you want, okay? Approach number 2. For example, if we have to do this structure here, okay? We can do, or in this way, okay? When we define the node 3, we assign the position, the coordinates, okay? In this case, it's just a 2D element, so just X and Y, and then quote unquote mass, the value of the mass, okay? Be careful that the coordinates are related to the dimension of the system, okay? In this case, it's a 2D, so you have 2 coordinates, okay? The masses are related to degree of freedom, since in this case it's a 2D, so we have 3 degrees of freedom. It's just a structural system. So you have to declare 3 different masses. Mass along X, Y, and rotation, okay? The same for the 3D case, in which you have 3 coordinates and 6 masses, okay? Otherwise, we can use the second approach, in which we declare the masses, the node, okay? So ID, and then here misses a comma, okay? X, Y, and then after we can declare the masses. So ID, the same ID, mass along X, Y, and rotation. Okay, is it clear? Otherwise, we can use another approach. We can define the masses when we declare the elements, okay? For example, with the elastic beam column that you saw yesterday with Cristoforo, you can declare the nodes, the area, and all the properties, okay? Mechanical properties of the element, okay? And then there is these optional parameters here, okay? In which you can declare quote unquote dash mass, the value of the masses, okay? How these masses are computed, we can see in this example here. It's just an example that you saw yesterday with Cristoforo. It's just a simple column. If we declare the masses like this way, of course, this is just one directional, but you have to declare
3 times or 2 times and 0, then you can, it's computed like lump must. So if the structure is this, the masses becomes this and this, become this and this, okay? Lumped at the end of the element, okay? Of course, pay attention that in this case, it's not just the value of the mass, but it's the value of the mass per unit length of the element, okay? If you have question, please stop me whenever you want. Also online, please unmute yourself and speak. So we know how to declare masses, how to run eigenvalue analysis. Pretty simple. With eigen, this command here in Opensees, you can define 2 different parameters to this function. First of all, the first parameter is the type of solver that you want to use. It's optional. The standard one is GAN band RPAC. The second one is the number of the eigenvalue that you want to compute. The results are just the lambdas, you know, that is just the square root or the square of the omegas. And starting from that, you can compute the period of the structure, all the periods of the structure. Pay attention that if you use the RPAC one, since it's use matrix-free eigenvalue analysis, it's a particular stuff that we are not going in detail about that, you can compute only the number of degree of freedom -1 eigenvalues, okay? Not all the eigenvalues, eigenvectors, but all the one -1, okay? If you want to compute all the eigenvalues, you have to use full the LAPAC, okay? That is way more slower. So it's just up to you. The default one is useful for, I think, 99% of the cases. Okay, so you have, for example, in this case here, okay, that you have 2 masses, you have, let's say, 2 modes. There are more modes, but it's other stuff. If you compute these masses only for X direction, for the horizontal direction, you have only 2 modes, let's say in this way. And so if we run eigen2 with the default solver, we have the 2 periods of the structure, okay? How to take the eigenvectors? For eigenvectors, there is another function that is called node eigenvector, pretty simple, in which you have to declare the number, the ID of the node, which eigenvector you want, and which degree of freedom, okay? For example, again, this structure here, if I want the first eigenvector value for the first mass here at the top, it's just eigenvector, the node 3, first eigenvector, degree of freedom 1, okay? Same for this eigenvector here, for example, it's just eigenvector node 2, okay? Eigenvector 2, direction, degree of freedom 1, okay? Direction X. Questions? Is it clear? Everything clear? It's pretty easy, I think, right? So if you wanna, we can try to do an exercise like this, okay? I think you can find all these exercises already in the portal. There is a zip folder with just all these exercises. This is inside the folder exercise 1. Here, there is a just 1 bay, 3 floors. Yeah, 3 floors structure, elastic one. Okay, so as the one, like the one of the exercises that yesterday Christopher showed you, in which I'll show you, I just declare the masses here. To all the nodes, I declare the masses in this way here. Okay, in the slide you will find how I compute the value of the mass. Okay, let me show. Okay, very fast. I'll show you
How is the structure? Okay, the structure is just like that, okay, in which this is the shape of the force, the shear forces, these are the axial load, these are the bending moment, and so on. Okay, pretty easy. The only difference is, okay, I just declare nodes, rigid diaphragm, restraint, elastic beam column elements, loads. Okay, you know everything about that now, yeah? The only difference is here, in which you have the masses. Okay, for all the node of the structure, I declare the mass that I computed just a couple of lines before. Okay, pretty easy. I have also a couple of slides about that. So okay, I just declare the masses in this way. These are the loads. Just one stuff. How to declare element loads. Okay, so loads along an element. There is a function in Opensees that is called L loads, pretty easy, in which you declare quote unquote dash L, the number of elements, and the type of force that you wanna define. For example, uniform with value Q. Okay. How to declare masses? I define the gravity acceleration. Pay attention to that stuff, okay? I have to be consistent with the unit system of the structure. In this case, my structure is defined in millimeter and seconds. So the gravitational acceleration is 9,800 meter over square seconds. And then I declare the weights and transform into masses and declare as lumped masses. Okay, pretty easy. The result. Okay, this is just a model, and here I run the gravitational analysis. Let's move to the model analysis. Okay, I just import the model. I just declare the number of modes that I want to analyze. OPS eigenvalue analysis with four different modes. Okay, and then omegas t as I showed you before. Okay, and here we can see the different modes of the structure. The first mode 0.6 second. Okay, the second mode 0.16, the third, and the fourth. Okay. To do this plot, I use OPSVs. There is a specific function for plotting the eigenvalue results. Okay. I wanna also show you how to declare. You can also run animation of your modes again with OPSVs with an in mode. There is a specific function for that. That now my computer is lagged, but okay. This is the animation of the fourth mode, for example. Okay. Or the first mode, there is a function called anim mode. Okay, you can see the animation of the modes. Pretty easy, I think, right? Questions about that? So how to declare masses, how to run eigenvalue analysis, how to take eigenvalues and eigenvectors. Okay, just three functions. Questions? If you don't have question, I want to show you another function. Sure. I don't know about that. Maybe you can save the figure as a GIF and then open it with the standard software for open figures. I don't know about that. Or you can set matplotlib to open a different an external figure like this. I think there is a command that is I don't remember the name of the command, but we can have a look that later about that. Okay. It's working now. Otherwise, you can save it. You can save it in your hard disk and then open it. Perfect. Okay, I want to show you another stuff. How typically when you run a model analysis, you want to know a bunch of parameters, a bunch of information about your structure. For example, the masses, and starting from the eigenvector analysis, you want to compute model coefficients, you want to compute model masses, and so on. Okay, so you can do that in Opensees by hand. Okay, I mean, you can take the mass matrix, you can take the stiffness matrix, you can take the eigenvector and do all the analysis for you that you want. Otherwise, you can use these other parameter, this other function, develop. I'm honored to that we share the room with the developer of this function. That is Dr. Petraka over there. Do all this stuff for you. Okay, so if you wanna, I don't know, the masses, model participation factors, model participation masses, and then a bunch of cumulative masses, model masses, and so on. Okay, you can use this function here. Okay, it's pretty easy. Just you have to call that function, and then you can declare if you want the results in a file, you want the results written in a file. Otherwise, you want to print on the screen, or you want to return in a dictionary, and then you can use it for your type of analysis. Okay, I'll show you how to use it. For example, printing in the terminal. Okay, I just declare with the option dash print, quote unquote dash print. Okay, and the function will give you a bunch of information. Okay, for example, the dimension of the problem, that is a 2D. Okay, the eigenvalues, the stuff that we did before by hand, you will find here. Okay, the total mass of the structure, free mass of the structure, the position of the center of mass. Okay, modal participation factor, modal masses, cumulative modal masses, and so on. Okay, a bunch of parameters that maybe you need for your type of analysis. Okay, otherwise you can here if you want, you can do in this way. So the results of this function here are inside this dictionary that I called modal prop. Okay, and for example, I show you how to take. It's pretty easy. Okay, it's just one value inside the dictionary. For example, the participation max along X here. Okay. Questions? Sure.
Chat box has loads influence in eigenvalues.
No. As this loads influence in eigenvalues? No, not at all. You have to declare loads and masses in the two different stuff. Okay. Pay also attention that, of course, if you declare different numbers that are not connected together, Opensees is okay with that. Okay. So we'll run gravitational analysis with one type of loads, and then as mass, another type of mass. Okay. So there are two different words: static analysis and eigenvector. Okay. Eigenvalue, eigenvector analysis. Okay. So masses are for eigenvalues, loads are for static analysis. Okay. And that's also the reason why you have to be consistent with the acceleration, the gravity acceleration. Otherwise, you will do a mess. Other questions? Also online. If there are no questions, I'll pass very quickly to the last stuff for modal analysis. Sure.
Can you explain why the folks their mass has 0 at the
Sure. But this is just in my case here, okay? This is just since I don't want to have a rotational mass, okay? Mass for rotation, degree of freedom. Okay? But it's just my decision. You can do whatever you want. You have to pay attention just one stuff, okay? The system is a 2D system with 3 degrees of freedom. So I have to declare 3 masses. If the mass is 0, I have to declare 0, okay? Is it clear, ZG? Okay, perfect. Okay, I have to declare a number of masses as the degree of freedom of the system. If I don't want a mass on that degree of freedom, I have to declare as 0, okay? Other questions? If there are no questions, I wanna ask you a question, okay? So
I show you. Oops. I show you this equation here, okay? That is the equation that you use for eigenvalue analysis, okay? Now we know how to declare mass matrix, okay? Any doubts about that? No, there is a stuff that is not clear in this way, in this moment. We know how to compute masses, right? Here. The mass matrix, okay? What about stiffness matrix? Opensees is highly devoted to nonlinear analysis, okay? What's the mass matrix that I have to use? Which stiffness? No mass, which stiffness matrix, okay? Yesterday afternoon, you saw that in Opensees, I can declare with different approaches nonlinear stiffness problems, okay? So which stiffness I'm using in Opensees when I compute the eigenvalue? Let's see with an exercise. I just borrowed an exercise from yesterday lecture from Professor Di Trapani. It's just a column, okay? It's exactly the same exercise that you saw yesterday. It's just a column fiber section with these materials, okay? And this is the results of pushover, okay? Which stiffness I'm using for computing eigenvalue? It's just the stiffness that I have in the moment I run eigenvalue. I'll show you in this moment. I show you with exercise 0. It's called in your folder, okay? Oops. Okay, the model is exactly the same of Professor Di Trapani showed you yesterday, okay? So it's just 2 nodes, the materials, the fibers, and so on, okay? I just run the gravitational analysis. After that, I just compute eigenvalue analysis here, you see? I just run the gravitational analysis and compute eigenvalue. Which stiffness I'm using? The stiffness at that moment, the moment I'm running eigenvalue analysis, okay? So for example, let me run this. For example, the first eigenvalue is 2.25 seconds, okay? What happens if I start running a pushover? For example, here.
So I'm running a pushover until 5 millimeter, okay? And then again, another eigenvalue analysis. What happens? You see, this is the shape of the pushover, okay? I'm running a pushover until 5 millimeters. I'm this point, okay? Which stiffness matrix I'm using? The stiffness at this point here for the eigenvalue, okay? So you see in the code, I'm running the pushover here, okay, until 5 millimeters, and then compute again the eigenvalue, okay? What's the value of the eigenvalue? You see, it's different. It's larger since the stiffness is lower, okay? Here, right? So I can do this stuff how many times I want. Oops. For example, I run for you. Here it's 2.25 seconds, okay? Here it's 2.64, but since the stiffness is changing. Here is 5.45, okay? And so on. Another question for you. Now answer, please. What happens if I run the eigenvalues analysis here at 25 millimeters? Some clue? And so? Yeah? And the eigenvalue analysis? Yeah, the stiffness is negative. And what happens to the eigenvalue? I'll show you here. Let's print just the lambda. Oh, oops. Not a number, okay? Since lambda is negative, okay? Yeah, the stiffness is negative. Since the structure is just one column, okay? The stiffness of the structure is negative. When I compute eigenvalue analysis, the lambda is negative. The period is not a number since, you know, when I just try to compute the square root of a negative number, the value is there is no number in the real set of numbers, okay? Is it clear? So pay attention to that. Eigenvalue, run the eigenvalue analysis with the stiffness matrix at the moment you are running that function, okay? So if I'm running here, I will find a negative lambda, okay? Since the stiffness is negative and so on, okay? Pay attention, you can use this trick here also during time history, the stuff that I'm gonna show you in a moment, okay? For non-linear systems. If the system is elastic, you know, the stuff is the same. The stiffness is the same during the analysis and you don't have problem. If the system is non-linear, like this, the results of eigenvalue analysis is just with the stiffness at the moment you are calling that function, okay? Questions? No questions? Yes. Yep.
This been running at the beginning.
Yeah. You can run, typically you run after the gravitational analysis. You apply vertical loads and you run eigenvalue, since, you know, the structure without vertical loads is not a real structure, okay? So you run vertical loads. After that, you run eigenvalues analysis, like I showed you here. Let's go back here. That is the simplest, okay? With just fiber X, I just declare everything of the structure, okay? Geometry, materials, sections, stuff like that, and then run gravitational analysis, okay? Here. Gravity loads, yeah. Depending on your structure. Typically for civil structure, you apply gravity loads. and then you run eigenvalue analysis.
Can it produce nonlinear also?
Typically, no. But depending on the type of structure that you're analyzing, okay?
Because we have assigned mass for the books. So should it be the actual beginning structure?
Let's try live. Vibration period before gravity loads. No. Let's run. Let's compare before gravity loads. Okay. After gravity loads, after 5 millimeter of pushover here. You see, in this case, we have some change in the stiffness due to gravity loads. Okay. So you see, before gravity loads is 2.0, after gravity loads is 2.25, after 5 millimeter of pushover is 2.6. So you have to compute eigenvalue analysis where at the moment you want the value of the eigenvector and the eigenvalue. Okay, of course the eigenvector will be modified, but not so much. Especially you will see that in the frequencies in the period of structure. Is it clear, this stuff? Any other questions? If you don't have questions, we can switch to the time history analysis. No questions? On the audience here, online? Of course, this is the same structure of Professor Itapen showed you, but with just the add of the mass. I just add the mass here of 150 Newton second over this square second. There is an error here, okay? Square second over millimeter, okay? Model properties, okay. Let's switch to time history. Again, here, the course is focused on Opensees. So all the theory behind, I am supposing that you know about that. But what's time history analysis? It's just the analysis of the complete equation of motion, equation of motion, okay? You have, yesterday you focus only on this part here, okay? On the stiffness and the displacements, okay? Before we add the masses and implicitly the accelerations, okay? Now we are adding the damping and velocities, and we are computing this equation, adding a ground motion input and a drag vector, okay? That declare the direction where that acceleration is defined, okay? So now the problem is how to compute this equation here, okay? What we did before is just neglect the damping and put this the left side of the equation equal to 0 and run a eigenvalue eigenvector analysis, okay? Now the problem is, let's add the ground motion input, okay? So the value of the acceleration that excites the masses of the structure here, okay? The masses are here in the mass matrix. So there is this acceleration of the ground motion, the acceleration at the base of the structure that excites mass. And then I have three components, okay? I have inertia, I have damping, I have response, okay? Stiffness response. What I need another ingredient in the recipe, okay? I have mass, I have stiffness. What I need? Damping and accelerations, okay? This is again the same stuff, okay? So I have mass, damping, I have stiffness matrix. No, wait, just 1 second, okay? Here, same stuff. Opensees is highly devoted to nonlinear analysis. In this case, it's elastic, okay? The stiffness is the same. What happens if I declare a nonlinear structure where the stiffness is changing during the analysis? It's changing both for nonlinear properties of materials, mechanical properties, or nonlinearity to geometrical nonlinearities, as Professor Ditapen showed yesterday. So corotational, P delta effect, stuff like that, okay? So in that case, the stiffness, okay, is just a function of the history of displacement and history of velocity, can be, okay? Mainly history of displacement, okay? The stiffness is updated every time. And we can call that restoring force, okay? K, the stiffness, times the displacement. Is the elastic response of the structure. So what I have to declare inside the structure? From model point of view, I need masses to compute the model mass, the mass matrix, okay? I need geometrical properties and of the materials. I need the geometry of the structure. I need linear, non-linear, of course. I need these are the ingredient of the recipe, that is the damping, okay, to define these other metrics here, okay. From analysis point of view, I need a ground motion, this term here, okay, and then recorders and a way how to integrate this function here, okay? We can do with a bunch of functions that I'm gonna show you in a moment, okay, in Opensees. Let's start with the first ingredient that we need, the damping, okay? Now, for the damping, we can talk about damping for hours, but let's focus mainly on the two dampings model that there are inside Opensees, okay? All the other comments about damping is out of the scope of this course, but in Opensees we have Rayleigh damping, okay? Rayleigh damping, you know, I think you know, it's just a linear combination of mass and stiffness metrics, okay? It's just a sum of the two terms, the two masses, the two matrices, with two parameters, alpha and beta, that just modify the weight of the two masses, the two matrices, okay? You know, it's just a particular case of Colgate damping for just the first two terms of the sum and all the stuff, okay? So it's just a linear combination of the other two terms that you already know, okay? You know how to declare masses, you know how to declare stiffness, okay? The only problem now is just how to find these two weights, alpha and beta, how to give the two weights to mass and stiffness to sum them. With easy math manipulation, we can find that the damping related to the critical damping ratio can be found as a function of the frequency of the structure, okay? So starting from this, it's pretty easy. You have to just pre and post multiply each term of this equation by the eigenvalues. You can do by hand in 2 minutes. You do you massage the equation and you find that in terms of critical damping like this, okay? So you have this first term that, if you remember, alpha here is the function of mass that is inverse proportional to the frequency. So you have this term here, okay? That is summed to the beta frequency divided by 2, but this is directly proportional, okay? It's linear. So you have this other term here, okay? What's the damping at the end? It's just the sum. So it's this curve, this black curve here in the plot, okay? This is just the sum of alpha m and beta k, okay, as a function of the frequency of the structure. How to find alpha and beta? Again, starting from this, you can fix two dampings and associate that two dampings to two frequency of your structure, okay? It's not two frequencies, okay? And if you put inside a matrix, you have a solution like this, you have a matrix like this. And if you solve this linear system, you will find these two terms, okay? Alpha and beta like this. It's pretty easy. You have to fix two frequencies and two dampings, Mn. Cm, Cn, the two dampings, omega n, two frequencies. After you fix that, you can find alpha and beta. How? This way. Again, the same. This evaluation is done for the same exercise that I showed before. So I'm just putting here as m and then the first and the third frequencies of the structure, okay, that I showed you before, and I'm fixing as critical damping 2% to both the frequencies, okay. You have a damping like this, right? In this, in the right side of the screen, I'm showing you the damping as a function of the frequencies, right? So I fix the first and the third mode to be 2%, right? And I found the alpha and beta, and I can compute the damping matrix, okay? Or the critical damping ratio as a function of critical damping ratio, okay? This is a typical way to do this type of analysis, this type of how to declare the Rayleigh damping. You have only to pay attention to one stuff. Rayleigh damping is good since it's how is good. I mean, why is good? Is related to the shape of the Rayleigh damping. You see, it's really high with low frequency, really high with high frequency, and then you have this convex shape. So you don't have negative damping, you don't have strange stuff that sometimes with some exotic damping models, you can find some strange behavior. Here, you don't have problem with that. The only problem that you have to pay attention to Rayleigh damping is that since the shape is in this way, if you fix two frequencies that are far away, you can find a damping lower here, okay? Like this, okay? If you fix the first, for example, first and third mode at 2%, for example, okay? Let's put a hypothesis that is a bare frame and I have a low damping, okay? With frequencies higher than the first mode, the damping is decreasing, okay? So, for example, I have a minimum here that is at 4 Hertz. That is 1.2, is significantly low than the one that I fix. So pay attention to that, okay? Pay attention to this stuff with Rayleigh damping. Why I'm saying that? I just spoiled the... Why I'm saying that? Since, again, K, we have to focus, every time we have to focus on K for Opensees, since, you know, we typically run linear analysis. Which K? Which stiffness? Again, is the stiffness at the moment I'm running Rayleigh damping? I'm declaring Rayleigh damping, yeah, or I'll show you that Rayleigh damping is posing this type of problem in a formal way. But again, if my structures decrease in stiffness, I can go to this point here where I have a lower damping, okay? So pay attention to this stuff here, okay? To solve the problem of which stiffness I can use for defining Rayleigh damping. The function of Rayleigh damping has been declared with different parameters. Okay, I have alpha, that is just the parameter that the weight of mass matrix. Okay, that typically mass remain the same during the analysis, so I don't have problem. Okay, mass matrix is fixed. Okay, is constant during the analysis. The problem is that which type of stiffness I'm using for beta. Okay, in this equation here, which type of stiffness? In Opensees, of course, if the system is linear, the stiffness, if the system is linear, the stiffness is the same, okay? So it's just the stiffness matrix. I don't have problem. I can use one of these three parameters, okay? It's exactly the same if I put, for example, this is alpha, this is beta. If I put this beta here in the third position, it's exactly the same, okay? But if the system is non-linear, what happens? I don't know which K. So this is the damping matrix, okay? Now it's just a function of where I compute K, okay? When I compute K. So in Opensees, I can declare three different types of beta, okay? The first one is with the initial K, okay? With the initial stiffness of the structure, just at T equal to 0. Okay, at T equal to 0, I use that tangent stiffness, I compute damping, that's all. Okay, during the analysis, the damping is the damping matrix remain the same. Okay, remains the same. Otherwise, I can use last convergence here, here, okay, in which I'm using the tangent stiffness at the step before. Okay, the last step I found the convergence, okay? Otherwise, I can use last iteration, that is last committed. So it's just at the step I'm running the analysis, the last iteration, I'm running iteration I, I'm using the stiffness iteration I minus 1, okay? So the same time step, the previous iteration, okay? So you can declare one of these, or if you are a pro version, if you are not a beginner, you can do some crazy stuff if you want. Like you can split the stuff into initial and then last committed, or you can do some analysis like that. Okay? Is it clear, this part? So again, in Opensees, every time I see stiffness, I have to, not in Opensees, in a non-linear model, okay? Every time I see the K stiffness, the K matrix, the stiffness matrix, I need a question mark, okay? Which stiffness? When? Which type of stiffness, okay? For example, in Rayleigh, you can define the beta related to which stiffness I want, okay? So initial one at the beginning of the analysis, the one at the previous step, the one at this step, but the previous iteration, okay? Questions about Rayleigh? Yes, no problem. How to design which matrix you want? It's up to you. I mean, you can decide to use the damping, the stiffness that you think is proper for your model, okay? Depending on if you wanna avoid this type of behavior, you can use the previous step stiffness, but you have to pay attention if you have strange behavior like higher damping, that high value of damping that you don't want during the analysis, for example, or if you are pretty sure that this problem of the reduction of damping due to the reduction of stiffness matrix, the stiffness value is not a problem for your system, you can use the initial tangent stiffness, or pay attention the last committed can be unstable. So it's up to you, okay? It's up to you which type of stiffness matrix you want to use. I don't know if Dr. Petraka has some suggestion about that. Which stiffness matrix to use for defining relay damping? Negative damping at that moment. Yeah, especially last committed, right? No, last committed. Like, sorry, the what's the name? Beta K. Maybe can be really stable since you can have negative stiffness and then.
But the end of the last step, it wasn't softening, it was negative.
So you have negative damping. I'll just repeat for the Zoom guys. So Dr. Petraka is suggesting that maybe it's better to use the initial tangent stiffness, right? Yeah, unless you know how is the nonlinearity of your model, right? I don't know if since you know that is the most stable tangent stiffness matrix that you have in during the analysis, right? Questions? Other questions? Okay, if you don't have questions, we can go to another damping. There is the second damping that you can define, that you will find in Opensees, that is the modal damping. Okay, modal damping is, you know, it's just defined like this. Okay, where mi star is just the modal mass. Okay, what is typically I mean, the theory is just that it's just the sum of all the modes of your structure. Okay, it's just the mode of your structure. For all the frequency of your structure, you define a damping value, again related to the critical damping ratio, and use the modal mass. Okay, and this is, if you see here, we solve the problem of the stiffness except for the frequency here. Okay, since we are using just the mass matrices, just mass matrix here, here. The stiffness is only here. Okay, but you can solve as we said before. What's the problem with this? That we typically don't have all the modes. What we can do is just fix a number of modes that I want. Okay, for example, with less modes of the number of the degree of freedom of my structures. Okay, so just for J modes, the first J modes, okay, I can fix a damping value. Okay, how to do that in Opensees? Really easy. Just modal damping. First, the damping has a critical damping ratio for the first mode to assign to the first mode, second, third, and so on. Okay, you don't have to declare for all the mode of your structure, just the mode that you want. For example, 3, 2, 4, and so on. Okay. There is a comment on Zoom. The stiffness to be used for relay damping as consequences in the obtaining structure response. There is an excellent paper that explains this very clearly and provides a recommendation to select the appropriate damping model depending on your structural mode. Charnayev, 2008, unintended consequence. Thank you so much for the suggestion directed. And there is another problem here. My question is from the last, there is an error before pushover when you find the eigenvalue analysis. My question is how to solve the problem. When calculate pushover yesterday, the warning disk. This is just, yeah, this is Faisal. This is just that the structure, your structure is having problem during the convergent problem, okay? So you have to check if maybe it's just at the end of the pushover and it's okay that you have convergence problems. Can't we use pointer or pen? Yeah, thank you, Omar. I'm sorry for that. I'm using the pointer here on the white screen, but I'll use the screen white. Okay, screen white. So Faisal, this is a convergent problem. Try to plot the convergent curve, the capacity curve, the results of the pushover curve, and the pushover analysis. And then if you still have problem that after iteration 1000, we can discuss about that after the lecture, okay? If you still have problem about that. Okay, questions about that? Questions about the damping? These are the two models that you can use it in Opensees, Rayleigh and model damping. Questions here online? Okay, if you don't have questions, let's go back to this slide. Okay, what we had now. Yes, please.
For modes, is it typical or you wanted to?
You can use them all for all the modes that you want. Okay, in this case, I'm just declaring for the first 4 modes, but I can declare for the first. Pay attention, of course. Yeah, in that case, it's just okay. Of course, maximum the number of degree of freedom of your structure. Otherwise, you don't have modes there. Okay. And Opensees will do all this stuff for you. Okay. All this stuff for you when you declare the. Other questions? Pay attention for higher modes, okay? If you wanna overdamp higher modes, that in Rayleigh damping is inside the model itself, okay? For higher modes, the damping increase, okay? For model damping, you have to pay attention of that if you wanna overdamp higher modes of your structure. Typically, problem for high-rise building that you don't want higher mode to have a predominant response, be a predominant weight during the analysis. Okay. Other questions? Online? Okay. Okay, if you don't have questions, let's go back to this. Okay. The ingredient for our analysis. We have, again, mass, as I showed you before. We have damping now. You know how to create a damping matrix. We have stiffness. You know how to do stiffness. The entire day, yesterday, for the entire day, we just discussed about stiffness. You know, all the stuff are related to stiffness. The stuff defined that we discussed about it about yesterday. Here we have again a mass matrix, pretty easy. The last ingredient that we need is just this, okay? So it's just the acceleration input, okay? How to do that? What we need? We need an input, okay? A ground motion input that can be inside a TXT. You can have in a list in Python. You can have inside a list, inside a dictionary. You can have wherever you want, okay? So, but you need a ground motion input, okay? The data from a ground motion input. You need the duration, okay? You need how long is the input, starting from which you can define how long is your analysis. That can be longer or shorter, as you want, typically longer, okay? Again, from the ground motion input, you need the time step, of the ground motion, okay? The frequency, the rate of recording the ground motion, okay? Starting from which, if you want, you can declare the time step of the analysis. That can be different, or maybe. I strongly suggest you to use a time step of the analysis smaller than the time step of the recording, okay? This is an example here on the right side of the right side of the screen, okay? So if the T, the red one, is the time step of the recording, the time step of the analysis can be shorter, okay? What happens, Opensees just interpolate the acceleration value, use that one, okay? But you don't care about that. Since you know each time step, you just run again all the integrator for integrate that function there. So you update the stiffness, you update the kinematic condition of the structure. So you update displacement, velocity, acceleration, and so on. Okay. And then in Opensees, you can declare in a formal way the scale factor if you want to scale the ground motion. I'll show you in a moment here. Okay. So what you have to do in Opensees, you have to use time series, okay, for defining the input. In time series, you have to define the ID of the time series, the time step of the time series, okay, where to find the time series, for example, here from a file, and here, of course, the name of the file, and the scale factor. I said before that you can use the scale factor since in Opensees you can scale automatically the input if you want. There is a problem with the arrow since this arrow will point here, okay? I'll solve it. After that, the time series, you can define a pattern like the one that you saw before, but in this case is a uniform excitation, okay? You define again an ID of that pattern. Pay attention that should be unique in your script, okay? So these are the typical error that you can do at the beginning when you start developing models in Opensees. You define again a pattern with the same ID of a previous pattern. For example, a pattern of loads for gravity analysis or stuff like that. Okay, so pay attention that should be unique, a different one. Okay, then you define the direction where that ground motion acts. Okay, you define that time series is acceleration. You are defining it as acceleration, and the ID of the time series. Again, here there is a problem with this arrow. It's just this ID here. Okay, oops. This ID here, okay? I'll upload again the slides in the portal, okay? So the ID of the time series, okay? Pretty easy. Other stuff that you have to declare is just the test for the integrator. Pay attention that they are the same for static analysis. Okay, you can use typically unbalanced displacement energy. You can use the norm or relative norm of that. Pay attention that with displacement and unbalance, if I'm not wrong, Dr. Petracca, you cannot use penalty, right? If you are using penalty constraint, you cannot use displacement and in the latest version, that's okay. Okay, so the next or the current one, the next release. Yeah. Okay, so the next release they will solve this problem. Okay, so but after I don't know, in some months you will yeah. Okay, so okay, so you have to declare the convergent criteria of the integrator, and you need another two stuff for running time history. Okay, you have to declare that the analysis are transient, is no more a static analysis, okay? You have to declare which type of integrator you want to use for solving the equation of motion, okay? For example, there are a bunch of integrators in Opensees: central difference, HHT, generalized alpha, that is 4 parameters, HHT, explicit, and so on, okay? The one that is typically used for this type of stuff is just Newmark. You know that you're behind, you have to declare 2 parameters, gamma and beta. Typically gamma is half and beta is from 1/6 to 1/5 or 4. If you use 1/4, the analysis is unconditionally stable. So I strongly suggest you to use half and 1/4. In this case, is unconditionally stable, unrelated to the dimension of the time step. Okay. Otherwise, you can use the integrator that you want, but pay attention in that case. Okay. For example, HHT has 4 parameters. Generalized alpha has 3 parameters. Sorry, generalized alpha with 4 parameters and so on. So in that case, have a look to the theory and pay attention on which type of integrator you're using, if the integration is stable and so on, okay? If you use Newmark with half and 1/4, you are sure that the solution is, the integration is unconditionally stable, okay? Just a quick stuff not for the beginners, okay? In Opensees, you can use also variable time step, okay? Instead of defining the time step fixed, as I showed you before, here, okay? You can define the boundaries of the time step, and then Opensees will change if there are convergence problems, okay? How to do that in analysis? You can define variable time step. You have to define a sublevel and the number of sub steps in the sublevels, and then you define the minimum, the maximum time step, and so on. Okay, but this is not. If you are at the beginning, don't worry about that. Let's move to the an exercise. Okay. Let's move to exercise number 2. Exercise number 2 is the same structure that I showed you for model analysis, exactly the same. I didn't change anything, okay? Geometry is the same, mechanical properties is the same, masses are the same, everything is the same. I'm just changing. So in X1, you will find exactly the same model again, okay? The model, masses, okay? Gravity analysis. Is super locked. Here you will find another script for the analysis of damping with relay damping that I showed you before, with some plots and stuff like that. If you wanna play with that. In time history, I'm just declaring the ingredient that I showed you before. So time step of the input, time step of the analysis, maximum direction of the analysis, and then just the number of steps. That's all. After that, I'm just declaring the test. In this case, I'm using energy increment, okay, with the tolerance of 1 to the power of 10 to the power of -7. Constraint, number, system, algorithm, Newton. The new stuff is just the integrator. I'm using Newmark in this case, as I showed you before, the integrator for the equation of motion. I'm just changing the type of analysis, in this case, transient, not static, okay? It's another word, okay? I'm just declaring Rayleigh damping, as I showed you before. In this case, I just call them alphas here, but it's just alpha and beta, okay? The 2 parameters of Rayleigh that I showed you before, all the stuff. And I'm declaring here as initial stiffness, okay? 1, 2, 3, the third parameter, okay? That's all. Time series, I'm taking the time series from a txt file here with a factor of 3, but I can change again to 1. Uniform excitation, ID, direction, 1, so horizontal. Type acceleration, which one? Time series 2, this stuff here, okay? That's all, and run the analysis. How to run the analysis? I take the time, I just prepare some variables to store the results, and then here I'm doing a couple of other stuff for stuff that I'm gonna show you in a moment, and then just that, okay? For all the time step, okay, if the analysis is converging, the last step converged, I just run one step with the T of analysis, the time step of analysis. If it doesn't converge, I'm just changing one algorithm, but you can do multiple algorithm changes if you want, and just modify from Newton to Newton with the initial stiffness in case I have problem. That's all, and I store the results. For example, one displacement, one reaction, and here what else? There is also something related to a stress strain, a fiber, and so on. No, not in this case. That's linear. Okay. Here I'm storing the results of the displacement for all the nodes. I need that for one stuff that I'm gonna show you in a moment. Okay, I can run it. If I want, I can print here the step, so we can see live. Acceleration is. No, there is a problem. Yeah, I just missed the acceleration file. I'll upload again in your folder. Linear. Yeah, I need the file of the acceleration right here. Okay. Okay. Now you can see everything lag, but okay. What happened? Meanwhile, Zoom just lagged. Okay. All the time step has been analyzed. For each time step, I just do all the iteration for the integrator for integrating the equation of motion, all the stuff related to the stiffness that in this case is linear, and so on. Okay. What I have at the end, I have all the recorders that I have, and also the displacement shape during the analysis. Okay, for all the time step there. Okay, you see for the time step 750, this is the deformer shape, and so on. Okay, I can do some animation. How to do the animation? Again with OPSVs. You will find the code inside in the folder. I think in exercise 2 the acceleration input file but I'll upload again in a minute after the lecture. Okay. From here, I can do all the post process that I like. Of course, this is the acceleration that I'm using. It's just acceleration input recorder, standard one. A strong suggestion: check the ground motion that you have. Check the time step of the analysis of the recorder, of the recording. Okay, of the input that you have. Check the unit length, the unit system. Check all the stuff in case modify it. Okay. Again, should be consistent with the acceleration of the input should be consistent with the system of unit of the structure. Okay, otherwise it's a mess. Yeah.
If we arrange the input data in other way, like here maybe time and acceleration, is there any other format that we can read?
For the ground motion, yeah, you don't need the time. The ground motion should be just the, I'll show you here. It's just, it just be a list of accelerations, okay? Just one column acceleration. If you're using a file, if you are import as a file, yeah.
You arrange it differently.
Yeah, you can define, as I said before, you can define as a list inside Python. So you have a list inside Python that you read like from a TXT or something that you have.
Yeah, five times or five in 5 columns.
You have to rearrange again to have just one list. Yeah, just one list. Yeah, you have to do that. You have to check. So this is a strongly suggestion for you. Check the ground motion that you have. It should be just one list of acceleration coherent with the unit system of your structure. Otherwise, it's not working. Okay. Other questions? Yeah, online.
With the rest of the the G values after they multiply the G with that, then you have to put it in the factor.
You can or modify the list of value that you have, or put as a factor here. Okay. For example, I'm using one since my acceleration are still coherent with the unit system of my structure. There are millimeter of square second. In my case, if there are G, I can put. Oh, sorry. I can write here. I can scale it with this parameter here if I want, or I can just pre-process and then import as acceleration in the unit system that I have in the structure. Okay, as you want. You can use the approach that you want, but that is a kindly suggestion for you. Check before running analysis. Check what's your input. Otherwise, you will start have problem that you don't understand what's the problem, and then it's just, I don't know, one missing number, a letter somewhere inside your input, stuff like that. It happens, but or just order of magnitude, just one acceleration that is like higher, but since you just changed the scientific factor, the scientific notation factor, stuff like that. Okay, so check the ground motion before running it.
So can we get the output in terms of certain decimal points? Because like here we have so many decimal points.
As input or output from? As output, yeah, you depending. If you use recorder, you can define the approximation. If you're using this sort of recording in Opensees Spy, like this stuff here, okay? I don't think so. You have to do like with the column.3f, stuff like that, okay? So you can declare the approximation, but not like this, otherwise an error. Yeah, you can do, but it's a matter of Python in that case. Okay, if you're using recorder, the standard recorder of Opensees, so right inside the file, you can declare there is a parameter that's called precision, if I remember correctly. Okay, so it's dash precision, and then you give the number of digits after the point. Okay. Otherwise, here is just up to you. I mean, inside the list, you have all the numbers. You have to do the. You can manipulate as you want as input. Okay, as output. Sorry, as input, more number you have, better is for you. Okay. Other questions?
Yeah, sorry. I have a question related to defining the variable data analysis, like the time for the analysis.
Yeah.
We usually do that in not specified in the analysis, but like creating a loop when there is non-convergence and then changing the analysis time or the parameters. So what's the difference between changing it in a loop and putting it in in the analysis function itself?
Here, I'm using this approach here since you know now the problem is elastic, so you don't have problem. But with nonlinear analysis, you can have problem of convergence, but convergence in the evaluation of stiffness, okay, structural stiffness. So when you pass from element stiffness, section stiffness, the stiffness of fibers, for example, and then go back to evaluate the stiffness of the structure, you can have problem there, okay? So maybe you need to change the algorithm for solving that stuff, okay? Maybe you want to change from Newton to modify Newton to Krylov Newton to all the algorithm that you have for evaluating that problem there, okay? So the stiffness problem. And so I'm just proposing you this approach here, but if the structure is elastic, we can use just that. That's a good point, okay? The structure is elastic. I don't need to change the algorithm. It's elastic. I know the stiffness, okay? I just need to compute all the time step, analysis time step, okay? Pay attention to that.
All right, thank you.
Okay, is it clear?
Yeah, thank you.
Other question about that? So if there are no questions, I can show you a couple of results. After that, you can do whatever you.
I have a question.
Yeah, sure.
Yeah, so like if I want to perform seismic analysis, like time history analysis for a scale factor 0.1 to 1.5, let's suppose, or any factor like for each 0.1 increment, then do I need to define different pattern and time series, or is there any other way?
Yeah, you can define different factors if you want. Pay attention how to store the results, since otherwise you just override the same results. Okay, you run again the model.
Yeah, that is the thing. If I want for each load increment or load factor, like from 0.1 to 1, maybe like 10 load factors.
Yep.
For each scenario, I want the load effects to be saved in a file. So do I need to create separate time series and pattern, or I can use the same time series and pattern with a simple loop on the factor?
Yeah. You can put the entire script that you have, okay? Or if you are a little bit more, you can do in a how to say smarter way. So just the geometry, put the geometry inside a class, and I don't know your level of Python. You can do some other stuff, but the main idea is that you put the entire Opensees model inside a loop and change each time the factor. Okay, so 0, 1, and run the analysis. Take the results, store somewhere. 0, 2. Declare the structure, declare the loads, declare the mass, run the analysis with factor 0, 2, take the results, store them. 0, 3, again. Okay, you can do that.
Okay, so you are saying that first I define a function within the program to create a model, then of another function for loading, and then a loop
Change
where
the
the
factor.
time series. Yeah, then for seismic analysis, I need to create a loop where I will call those functions and run the analysis. And for each scenario, I will save the file. This is what you are saying. So the question is,
Pay attention to the name of the file that you are saving. Otherwise, you overwrite every time. So inside the name of the file, if you are using a recorder, you have to parameterize the name of the file according to the factor that you are using. Okay. So
yeah, I completely got your point.
pay attention to that.
Question is, do I need to have separate time series? I mean the name, the tag of the time series and the tag of the pattern. Do I need to parameterize those two as well, or I can use the same number?
Depending if you are running again the entire Opensees model, so at the beginning of your loop you are putting OPS wipe, for example, to remove the entire model that you declare in the step before, you can use
Okay.
the same ID.
Okay.
Since
If I am not pipe, then
if you're not,
I
you can do something related to changing the ID of the time series and then time pattern, but it's a little bit more tricky. You have to pay attention to that. So just take the structure, and you have to clear also the history of the structure. Is not so easy. I don't think you can do that, but the easiest way is just to run the entire script from the beginning. Okay, so you clear your Opensees model, you run it, you declare the geometry, declare the mechanical properties, declare the loads, run the graph, the analysis, run the time history. Okay, take the results, clear everything, and start again. That's the best approach.
okay.
I think
So
the easiest way.
better is for each load increment I create, I mean save as the input file, the Python, OpenSys Python file separately and run it separately, take out the load effects and work according.
And
That
then
is the best
write
you are
another
saying.
script for the post process to read all the results and do whatever you want with that.
Okay, okay. Another question that is
Yep.
related to if I want to perform incremental dynamic analysis,
Yep.
then how should I proceed?
In this way, you have to. I mean, you can do other stuff. Okay, is it clear the part of increment the factor? If that if that stuff is clear, you have to just put this entire script, okay, with the loop for all the factors inside another loop for all the gram motion that you need. Okay, so you have, I don't know, 100 gram motion, and you want to analyze each gram motion for 01, 02, 03 up to, I don't know, 5.
Yeah.
You have the script that runs 1 gram motion for all the factors. Okay, put that script inside another bigger loop that change the gram motion. Pay attention how to store the results, and you have done with and everything's clear. Now everything is ready for running on IDA. Okay, since you have to change the gram motion, for each gram motion you change the factors, and you have to run it now. Pay attention how to store the results, and then you have to do a script for post-process these results. Okay, so read each file and see what's going on.
Is there any training video or example video on the same incremental dynamic analysis for multiple seismic acceleration and different load factors or something like that? Any one of the two parameterization? Is there any training or
I understand the
example
question.
video?
Yeah, sorry, can you repeat the question again? What's the question?
Question is, if the procedure you told me, if there is any training video or example video, it would be very helpful. So is there any
Training about that? Maybe. I don't think in Opensees.
any video related to the same, like incremental dynamic analysis, how they are performing? I tried to find out in YouTube, but I couldn't.
I don't know about that.
Any documentation
for Opensees? I don't know. Maybe
okay.
you can try to do something, and if you have problem for something, send me an email. We can discuss about that.
Sure.
I mean, I did also in IDA. It's not complicated. If you think about that, you have to just change two stuff: factors and gram motion. So try to do that. If you have problems, send me an email. Okay, and we can discuss about that. Okay.
Sure.
Other questions?
Yeah.
Okay, if you don't have questions, I'll show you a couple of results that you can take from time history. for example, I can take the story of displacement for different nodes with maximum, for example. I can take the drift profile. I can take plots of drift over best shear and so on, okay? I can do all the stuff that I want now. Since I have the history, I have the displacement, I have the stresses, I have the forces, I have everything on the structure. It's just now a matter of what I need to do, okay? Very briefly, I want to show you how that you can do the same type of analysis just for a nonlinear case, okay? I just modified, this is exercise number 3. I just modified the geometry. No, the geometry is the same, okay? I just modified the mechanical properties with, okay, concrete 0.2 and steel 0.2 for the steel. I just declared fiber sections. I just defined force beam columns. Okay, it's just the same model but non-linear with these properties here. Okay, with this section here, these mechanical properties here. Now it's pretty easy. I just need to run it again. It's super lagged, but okay. Again, I need the acceleration file. Can I send you the file? Oh. Okay, can I upload the? Thank you so much. Now we are uploading the file. Okay, so the stuff is the same. The only stuff that I'm changing here is that stuff of the change of algorithm if I have non-linear or if I have non-convergence of non-linear problem. Okay. Then the problem is exactly the same. I just forgot to. If you want to see the animation, you can run the animation and so on. Okay. What I can do now is just limited by imagination. Okay, now it's still running. Okay, and you can find, for example, it's super lagged, but in your computer you will see it without any no, it's running now. Okay, if you want, you can take all the values that you want. You can do all the plot that you want. You can do all the comparison you want. Okay, for example, we can compare. We can compare, for example, the displacement history of some nodes. Gray is the previous one, red is the nonlinear one. We can compare the drift profile. We can compare force drift plots. We can do, now it's just, now you have to be, you need to have the idea clear of what you want and what you have to do with this type of analysis, okay? Which type of parameter you want to check, which limit you want to check, which limit state you want to check, how, okay? Now it's just up to you, okay? Any question about it? Question online? Oh, a bunch of questions online. Okay. Thank you so much for the. Okay, if you don't question, the last 5 minutes I want to talk about 2 stuff, okay? First of all, a couple of hints or stuff that you can do with time history. What we saw is just uniform earthquake, uniform excitation like this, okay? In Opensees, you can do also bidirectional earthquake excitation by your tree, okay? You can also add the vertical, okay? You can do this type of analysis exactly as it is for 3D model, okay? With all the stuff that Professor De Martino explained yesterday for the 3D, but from analysis point of view, the stuff are exactly the same. Pay attention to which degree of freedom you wanna apply the acceleration, okay? Other stuff that you can do is multiple support excitation, for example, bridges, pipelines, stuff like that, okay? You wanna change the ground motion information along your structure, okay? Typically stuff is for bridge piers or pipelines or long infrastructures, stuff like that, okay? It's pretty easy how to do that. You will see in the documentation there are all the stuff. You have just to change the type of analysis, pretty easy. And of course, you have to declare multiple ground motion input, okay? Another stuff that you can do in Opensees, thanks to Dr. Petrak again for this, is to run response spectral analysis. It's just another function as the modal parameter that I showed you before. In this case, you just define your spectrum and run the analysis, and you will then it's up to you how to combine the results. Okay, you want to use SRSS, CQC, or stuff like that. Okay, you will run this type of analysis pretty easy. You can do by hand using also modal parameters function, or with this function is just a matter of 3 lines, okay, of code. Then you have to post-process the results, and it's up to you, okay, how to combine the results. Okay, this is just a couple of hints. If I have a moment, I want to show you one stuff, okay? The last question of today. Again, you have to talk. Sure. Bidirection is pretty easy. You have to define 2 different time series. One for degree of freedom 1, one for degree of freedom 2, the other one the other degree of freedom. You have to pay attention to the pattern. And then it's exactly the same. You have to take the results, okay? Other questions? For multiple support, you have to pay attention to how to declare the degree of freedom, how to declare the stuff. It's not so straightforward, okay? Multiple support. But in the Opensees wiki, you will also find 3 or 4 examples of that, if I remember properly, okay? Again, this is a stuff of the analysis, the structure, how to define the structure. It's up to you. You can define linear, non-linear, with fibers, with force base, with displacement base. It's up to you, okay? For analysis point of view, you have this option here in Opensees. Other questions? If there are no questions, I have 2 minutes. I want to ask you another stuff, just to conclude. Okay? Yeah.
Yeah. So
Otherwise, people can think about. Yeah. Go ahead.
Yeah. The question is, like, if I am doing an analysis, let's suppose for a structure which have a pile foundation.
Yeah.
Then, and I am modeling the piles
Yeah.
and providing equal DOF and zero length element for soil stiffnesses and all.
Yeah.
Then when I am I want to perform the multi-support excitation or uniform earthquake excitation, then
Yeah.
how should I apply into the model? Should I apply on each pile nodes or on a particular node at the bottom of the pile, or
Mm.
you are getting my point? Like if I have 5
Yeah.
piles, each pile have 20 divisions, like 20-meter depth, then how should I apply the
Excitation.
excitation force into the structure, onto the pile foundation? In general, the idea is it will come from the ground and go up. So if I have 5 piles, not a single line, then
Yeah.
how should I apply uniform excitation force?
Yeah, I think you can apply to all the node. I mean, I'm not a geotechnical expert. I'm not into that topic. So if you have different piles, you can define, as in this case, okay, I just apply the to all the masses. You don't care about that if you want, okay? But then it's up to you. I don't know geotechnical details about how to run piles analysis.
No, it's I'm not talking about how to run
This
pile
afternoon we have a lecture about geotechnical analysis in Opensees, okay?
Okay.
From geotechnical point of view, I'm sorry, I cannot give you any advice about that. From structural point of view, I mean, Opensees doesn't care
Yeah,
what type of
I want
what
your
type of
opinion
analysis.
from structure point of view. not
You have to ask, this afternoon we have an entire lecture about how to perform geotechnical analysis in Opensees. Okay, so you can ask there if you have geotechnical details about that. I'm sorry, on that I cannot help. Okay,
Okay.
ask this afternoon. Other questions?
Yeah, sorry, I have a small question related. Before we do any seismic analysis, we first perform gravity analysis.
Yep.
And for example, for the beams, we apply the loads, for example, using LE loads. But then LE load works only with linear and P delta transformations. So when we perform the dynamic analysis, what if we want to account for the large displacements? Well, how to tackle this problem?
Which type of problem? Maybe we cannot hear you properly.
Yeah, sorry, can you hear me better now?
Yeah, maybe.
Yeah, so we apply the loads for the beams, for example, in a structure using LE load. Yeah.
Yep.
And then we perform the dynamic analysis.
Yeah.
But if I want to account for large displacements, then I should use co-rotation geometrical transformation for the beams.
Yeah. If you want.
But co-rotation doesn't work with LE loads. Like LE loads doesn't work with co-rotation. So how to tackle this problem?
Are you sure that co-rotation is not working with it? But you think you have to think about that. LL load is just split the load in the nodes of the element. So after that, it's just a nodal node. Is an easier way for you as a user to define the loads. But
Okay.
if you have problem about that, we can discuss also with Dr. Petrak later on.
All right, thank you.
Okay, but I don't think it's a problem to use LL load with co-rotational. But we can discuss about it. It's not working co-rotational with a load. In that case, you just split the loads in nodes, right?
Yeah.
Please.
But I was asking if there's another solution for that.
Yeah, just split the loads into the nodes of the element. That's the same.
Okay, thank you.
Of course, all the bending moment diagrams will be different, but from finite element point of view, it's exactly the same problem. Okay.
All right, thank you.
Of course, when you plot the diagrams there are strange, but it's another stuff. Okay.
All right, thank you.
Okay, no problem. Really, 1 minute. No, it's just 1 minute. It's just for a joke. Okay. Now it's not. I have this problem here. Okay. I have one node. Okay. Just one node. I have a force. Okay. In a global coordinate system like that. No beam, no restraint, no shell, no quad, no nothing. Just one node. Okay. No restraints. Okay. And I'm asking you, what's the displacement on the node? What's the force on the node? Come on. What's the displacement on node 1? Louder. Come on. What's the displacement? Infinity? How? How you said infinity? No boundary, no restraint, no constraint, no stuff. I'll change the question, okay? How you compute infinity? Maybe, oops, this way? Okay, displacement is the inverse of stiffness matrix times the forces. But what's the stiffness of this structure? Yeah.
There is not any stiffness. It's
no stiffness. Zero. Okay. Let's change the. There
will be a free fall.
Yeah, but you're thinking as a structure engineer from static point of view. Okay. let's think about transient point of view, okay? From transient point of view, the question is not what's the stiffness. The question is when, okay? This system, from static point of view, it cannot be solved. It's not well posed, okay? From transient point of view, this problem can be analyzed in this way, okay? I can solve the problem, okay? I can solve the problem, the equation of motion, and I have the solution, okay? This is not a fake animation. Okay, I can solve this stuff here with no damping, no stiffness, but the system can be solved. You don't trust me? I solved in Opensees. There is another hidden folder in Opensees in the stuff that I'm gonna upload you. Okay, just you see, it's just an Opensees model. I just declare one node with masses, just 2 degrees of freedom. I don't care about rotation, okay? These are other stuff. I just two dimension, 2 degrees of freedom. I just neglect rotation, okay? Time series, I just put a load, you see? Opensees, okay? Integrator, as I showed you before, I'm using Newmark. I'm just declaring a transient. If you wanna just have a look, try to do that with static analysis. Opensees will fill you of warnings and errors, okay? Since Opensees doesn't have a stiffness metric, I cannot inverse a stiffness metric that is not declared, okay? There is no stiffness metrics. So if you run with static, you won't have analysis of that. Opensees will fill you of warning and errors, okay? But if you run as a transient, okay? We are running the analysis. I'm running the analysis here. I'm just taking the results as X and Y, okay? If you want, we can just play with that. We can put some acceleration with just initial velocity, okay? Just showing some other stuff with just 1 theta, okay? Just running, just firing a firework, okay? Okay, and I have the results. I can change the angle, I can change the velocity. This problem is not well posed, okay, from transient point of view, okay? Since I have this equation here, I can solve this equation, I have everything, okay? So I borrowed this example from Professor Scott blog, as Professor De Martino talked about yesterday, just to say one stuff. Time history are a great tool. In Opensees, they are easy to set, they're easy to analyze. You don't have to care about integration. You don't have to care about a bunch of stuff, okay? With just one line, you can declare Newmark instead of writing lines and lines of Newmark integration, okay? You can run nonlinear analysis that is pretty complicated with time history, okay? But be careful. Otherwise, you can have stuff like that, okay? That doesn't have means from structural point of view, okay? We just 2 minutes late. We just end with this lecture. If you have questions, we can discuss about something. I think now we have coffee break, right, Professor De Martino? We have coffee break, 50 minutes. And then I kill them with time history. It was heavy. I mean, I tried to split in small slices to be easy to make them easy to digest. But if you have question or problem about that, please ask me, or later on during the live workshop that we will propose you an exercise about that. Not the firework, okay? Just a real structural stuff. And that's all. Okay, thank you for. See you in 15/20 minutes, okay? For the next lecture.
Okay, we can restart, I think. And we have roughly 1 hour. So what I would like to show you today is some introduction about parametric analysis and how the parametric analysis is then propagating in the optimization problem in general. I think is a, let's say, is a minor content because it's more a programming stuff we will see today. Generally speaking, if you have seen yesterday, I recommend you to use always the inputs to define your function. So start with the input, then define a code, and then do some function. So today we will learn first how to make a parametric model. Is quite common to perform parametric modeling. For instance, we will start from this problem. Let's say you have a frame. As you learned from my lecture yesterday, the idea is that we start with a simple one, so then you can extend your problem and build up from this problem as making as complicated as much as you want. Let's say you want to build a parametric frame. So in this case, yesterday with me, we have seen an elastic frame, but I think the concept is exactly the same. In this case, we want to change, for instance, the number of floors and the number of bays of the frame. For instance, in this case, you can see represented a frame with 2 stories and 2 bays. And in this case, the height, okay, represented here by L, and the span width is the constant. So we have L and L2, and we have a certain set of force applied. So first of all, since this year we are in this transition course between TCL and Python, probably for the future editions, we are planning to have full Python editions. I would like to show you how complicated it can be to build a parametric model inside TCL. Generally speaking, my recommendation is the following when you want to build a parametric model. Please first think what you want to build. Okay, in this case, we clarify to each other that we want to build a frame by changing the number of span and the height. After this, try to think an appropriate way to call the nodes and the elements. As you can see, for this example, this is the example developed in TCL. I will show you a slight different notation when I'm dealing with the Python code. There is a clear logical order in the numbering of the nodes, right? So I'm starting from the node in the bottom part, right? The one here, located at the beginning of the reference system. And as you can see, this node is called 1, 1, right? 1, 1 means first span, first floor, okay? Level 0, basically. Obviously here, and I will show you another trick I used in Python edition, you have to start from 1, right? You cannot call a node 0, 1, right? Because 0, 1 means 1, right? So always the first number must be, the first digit must be 1 in this notation. As you can see, when you move here, you have 1, 2, and then you have 2, 1, and so on, okay? I use a similar notation for the beams and the columns. You can see here 1, 1 is representing the first column, 1, 3 is representing the second column, 1, 5 is representing the third column. Obviously, the notation is 1 is representing the floor. The second number basically is representing plus, you can see the plus basically 2 is representing the location of the column. Similarly, we have the beams, right? So you're moving from column 1, 1, 1, 2, 1, 3, 1, 4, and so on. And similar in the second floor. In this way, you have a clear understanding, and you can build in a parametric way, which means, in other words, to build a series of 4 cycles, okay, to define your structure, your structural system. So how to do this in TCL? So first, if you want to build this structure in a non-parametric way, yesterday we have seen this introduction. I think you should define again the variables, right? Similar to what we did yesterday. Is a 2-dimensional problem. We build the model. You can see here again we have 2-dimension and 3 degree of freedom. And in this case, we start to build the location of the nodes. So it's very easy for you, I think, to understand that we have 1, 1 is located at 0, 0. For instance, 1, 2 is located at L2, 0, right? If we go back here, right, it's clear that 1, 2 is located and so on, right? The first level, they are located at the height, or if you want, y coordinate equal to 0. The second level is located at the height L multiplied by 1, and you can see the third level is located at 2 height, right? Obviously, it's easy to move from this logic, okay, to a parametric logic if you build your system in a proper way. So you can see here that, for instance, I can open the code, okay, with the equivalent parametric representation. I will open this code, okay. In this case, the difference is that we are defining, okay, let me change this number to be consistent. A number of story equal to 2, a number of base equal to 2. And instead, you can see of using the code that we are using a series of cycles. So this is a typical cycle. We have seen an introduction yesterday in TCL. So you can see we start, okay, by setting, okay, the variable y equal to 1. Then we are selecting an ending condition where we say that y should be less than the number of story plus 1. Obviously, 1, 2, 3 means for y equal to 1. At each step, we are incrementing y of 1 using this. Then we have another nested cycle. You can see we have 4, where we are again resetting the x. Okay, the x coordinate is the horizontal coordinate. X coordinate must be less than the number of base plus 1. Again, at each step or at each iteration, we are incrementing this x of 1. And if we, let me only go a little bit here, we go down, right? And at this point, you can see we are appending, you can see here the location of the node and evaluating this. So first we are creating a string here with you can see the node, okay, we call this D, okay, where we are creating this node. We are setting the format, okay, yx is the name of the node, and then we are selecting the location here of the node. We have also created this variable called plot puts. So basically it's a variable to define if it's equal to 1, you will see the output, okay, of this series of strings that are evaluated on line 44 by each of the iterations. And at each step, okay, we are canceling, okay, this temporary variable D. So basically in TCL, the common approach is the following. First, we cycle on the number of base and number of spans. We created a variable called D containing a series of strings, okay, with the code, basically, node and the positions and tag of the node. We are evaluating this D, so this means we are evaluating and creating the nodes. And if this plot puts variable is created, what we are doing basically is to print the variables D. And then we are unset, so we are deleting this variable D. You can see very well that if we, for instance, run this code, okay, sorry, let me make this bigger for you so we can run this. Since the variable plot puts is open, we will see the output of this, okay? So I will go a little bit up. So you can see that the code is creating this series of nodes. You can see here, the node 1, 1 located at coordinate 0, 0. So here, this is simple, the string that then is evaluated inside the code. The node 1, 2 has a coordinate 3000, 0. The node 1, 3 has coordinate 6000, 0. Obviously, we can go back. The coordinates are evaluated according to these parameters here, okay? L 5000 and L2 3000. Therefore, the first the node 1, 2 is located at 3000. The second node here is located at 6000, right? So if you go to the second floor, node 2, 1, 2, 2, 2, 3, you can see we have exactly the same logic, but everything is changed of coordinate 5000 in the y direction because we have the second floor, and so on. We can build in this way. After this, I mean, if we continue the code, okay, by adopting a non-parametric version, you can see what we are doing is to fix, okay, fix 1, 1, fix 1, 2, fix 1, 3, okay, creating 1, 1, okay, basically fixing the 3 nodes. In the parametric version of this code, again, I think if you can understand this logic, right, We have, obviously, I put on line 49 these puts to make an empty line, okay, to divide the information between the two. So you can see here that we have basically a fix, okay, only considering the first bay. So you can see here that we are only iterating on x, so in the x direction. So this means in the horizontal direction, we want to block the 3 base nodes. And we are, again, appending, creating this temporary string variable called fix, and creating, you can see, this fixed condition where we are fixing the node with coordinate 1 and variable coordinates. So on the other end, we want to fix 1, 1, the node 1, 1, the node 1, 2, the node 1, 1, 3, and so on, right? All the nodes located at the base. And we want to fix 1, 2, 3, all the degree of freedom. So at the end, we are evaluating again the variable d, and we are again plotting the content of this variable. So as you can see here, I am creating this block, right? Here, I'm fixing 1, 1, the 3 degree of freedom, the translation along x, the translation along y, and the rotation. And I'm doing this in an automatic way. At this point, I will switch to the non-parametric way, okay? Again, what I'm doing is creating, you can see, the geometric transformation linear, okay? Again, we don't have to specify the orientation of the cross-section because it's a two-dimensional problem. And you can see here, we are creating the elements one by one. So first here, you can see the representations of the different elements of the first floor. Obviously, if you remember the notation, this is the first column, this is the second column, this is the third column, and this is the beam, and this is the second beam, right? So you can simply look here, right? 1, 1 is the first column, 1, 2 is this beam, 1, 3 is this column, and so on, right? So these are the elements located on the first floor, and these are the elements located on the second floor. Obviously, here I'm assuming, okay, that the area, the inertia, and the elastic modulus of all the elements is the same, but it's quite easy to change this code, obviously, creating a series of lists to change it. So in the parametric version of this, we are following exactly the same logic. We are creating a single, I'm waiting for the update. We are creating a single geometric transformation. You can see it defined on line 65. And then we are moving, you can see, creating this iteration again on the two direction, on x and y, okay, where we are creating this temporary text variable d with the format, okay, of the inputs we have seen before, right? Exactly, elastic beam column, the string, okay, representing the tag, okay, this means, for instance, 1, 1, 1, 2, and so on. The location of the nodes, okay, here, so the first node connecting and the second node written in a proper way, okay? And finally, okay, we are evaluating this. So if you look about the results of this score, okay, you have a similar, okay, logic, okay? We are creating, okay, here all the elements of our structural system, okay? At the end of the day, okay, we are, for instance, evaluating, okay, a certain displacement in a specific node, for instance, here, the node 2.1. So what is the advantage of this code, right? That if I want to, okay, obviously the load is exactly the same. You can parameterize, okay, also the application of your specific load. And you can also parameterize if you want and save whatever information is needed, okay? So what is the advantage of this parametric version compared to this version? That in this case, if you want to evaluate, for instance, a bigger building like 4 by 4, okay, it's very easy, right? You can rerun, okay, here the code, right? I can digit clear, okay? So we can clear it, so we can make Opensees, okay? And for instance, you can rerun this code, okay? And you will see that the structure, okay, is much more complicated in this case, right? We have different number of floors, right? We have 5. I think I changed to 4, 4, okay? We have 5 columns, you know, and we have different stories, okay, in an automatic way. And directly, okay, we can calculate the displacement of a specific node, okay? So in this way, basically, when you have a representation in a parametric way, you have a function. So you have a function, you enter with a certain number of parameters, and you can have a certain output. Okay, completed the exercise 1, okay. I would like to move now to Python. I think Antonio was fully in Python, right, the lecture. I think you fully switched to Python, but I keep some connection to TCL. But I keep this first exercise in TCL more to show you that it's much more complex to program in TCL, right? So you will see how easy it is. Okay, before to move, okay, let me close these examples here, and let's move to our lovely friend Spider. Okay, let me close everything here as well. Okay, I want to restart and have a brief recap of the exercise we have seen yesterday regarding the frame. Only 1 second. First lecture, De Martino. Okay, so here we have the frame elastic. Here. Okay, I can close this. Okay, so yesterday we have seen this simple example. Okay, in this example, yesterday, I don't know why I'm fighting with my computer. We created, you can see this very simple structure here. And again, we created this structure here. You can see by basically programming in a similar concept, okay, the location of the node and the fix one by one, okay, and creating the structure. Okay, you will find a similar parametric representation, okay, in the code. If you go to second lecture and you open the exercise 2, it's called frame elastic. You will find a similar code representing, okay, the structure in a parametric way. Okay, in this case, you can see we can easily create a 2x2 story frame. Okay, you will see it's exactly the same. Okay, in this case, I'm creating a 2x2 story frame. We will see that we can create easily whatever sides of the frame. Again, the assumptions is that the span is a constant, but if you want, we can do real-time modification. We have simply to make a list, okay, and read the list, and we have the same height, is 3 meters in this case. Okay, you can see here that the tag I used compared to the TCL example is a little bit different. This is something now I'm using also in my research commonly. I mean, this way to give a name to the nodes and elements. But I will show you now in a while how to achieve these results. Okay. The structure is exactly the same. Again, we change compared to the non-parametric version by adding this number of stories and number of bays. And again, we created some loops. Okay, let's have a look about these loops, okay? Here we have this loop, okay? I think you can see compared to the TCL is much easier to read this loop. I think Python is a very easy code compared to TCL. So you can see here, let's have a look about the loop. Okay, then we have a look about the function creating the naming. So the loop is very easy. So we are creating a variable I. Okay, before it was called X, but the concept is exactly the same. This variable I, you can see, is ranging from 0 to n base plus 1. So n base plus 1, because basically we have, if we have 2 base, we have 3 nodes, right? So we have 0, 1, 2. Remember that normally in Python, the 4 cycles are starting from 0, okay? So when you are running this loop, okay, we can have a look together. You are starting from 0, okay? Let me show you, it's easy. So tag, print, I, so we can see this loop. So you can see we are 0, 1, 2. 0, 1, 2, obviously, we are iterating with 0, 1, 2. This means the 3 direction, okay? So then we are also iterating, J is the vertical direction, and we are iterating from 0, 1, 2, right? Because we have 2 stories, so we have 3 nodes, okay? At this point, that's my trick. I created this function called node name. I think that's a very nice way to define nodes, elements, and so on. So this is a function, basically having as an input the values I and j, and transforming, okay, this I and j into a string, okay, as you can see here, with the number 1 in front of the string, again, because the tag must start with 1. So whatever is 1 in front is representing, you can see here, the node, okay? So all the tag of the nodes you can see starting with a 1 in front. And with the first 2 digits, okay, this is the meaning of 2D. This means transform into a string, okay, with 2 digits. With the first 2 digits, you can see representing basically the, after the 1, obviously, representing the coordinate in the x direction, or if you want called I, and the second 2 digits representing the coordinate in the vertical direction. So basically here we created a parametric version of the coordinates of the nodes. So at this point you can easily understand it, right? Because if you read the 10, 0, 2, 0, 0 means a node, okay, because it's 1, sorry, on the second, okay, span, okay, starting from 0, okay, so 0, 1, 2, and located at the ground level, right? Because it's 0, 0. What is the limitation of this? The limitation of this, but you can extend this, is that the maximum number of nodes you can have is 99, obviously, right? Otherwise, you can increase this, okay, to have 3 digits, okay? If I change this to have 3 digits, right, you will see 3 and 3, you can have 999, right? You can see that now it's a little bit longer, but I think we can read on the floor, right? Now we have 1, 3 digits, and 3 digits, right? In this way, you can have 999 nodes in each direction, right? You can define it this way, okay? So I think it's difficult to have 999s in normal structures, but I think in theory, you can modify by yourself. You can have also much more. I don't know what is the limit of the length, I think, at some point of the tag, but I think obviously there is a limit. But in any case, I think this is a good way to show, to represent your structure. Okay, I think so. You can see only to be sure that we are on the same page. We can, I mean, evaluate this function. This function is very easy. Okay, so also by hand, right? You can use the function like this, 1, 1, as you can see, is giving you as back. There is some delay again. There is giving you 1, 0, 1, 0, 1. Okay. Okay, that's the trick. Okay. I will follow this trick in all this presentation, okay, regarding this parametric frame, okay? Because I have a similar trick now you can understand for the columns. The difference is that for the columns I'm using, for columns and beams, I'm using 1 in front of the columns and 2 in front of the beams. So directly when you have an element called with 2, you can understand that it's a beam. When you have an element called with 1, you can directly understand it's a column, right? So, and the logic is exactly the same. I don't think it's so complicated at some point, this logic. So you can see here, right? We define, okay, first the boundary conditions. For the boundary conditions, we want to fix the base nodes. So here the code becomes super easy, okay? We have, you can see here on line 54, 50, I lost myself here. 54, okay, we have for I to the number of base plus 1 because we want to fix the base nodes. J is always 0 because we want to refer to this, and we have fix. We can reuse this function to recall the node, okay, with ij, and we want to fix all the base nodes. So at this point, again, is a linear problem with a geometric linear transformation. We don't want to use any complex stuff like Tony's Berna when he used the connotational stuff. So we define again 2 functions for the column name, beam name. These 2 functions, as you can see, they have exactly the same logic of the node name function. Again, they are transforming the number into strings. They are merging the strings, and they are putting a number in front. In this case, 1 from the column. You can understand this 1 from the column, and the 2 from the beam. I think it's very important to think in this way because then it's very easy to understand the numbers in the model, right? Because sometimes, you know, especially when you have a complex model, you can extend this concept obviously in 3 dimension. I did the same in 3 dimension, right? You can have a K, for instance, coordinate, ijk, right? And you can build a 3-dimensional structure. But in this way, you can control the code in an easy way. So, and you can see here, we have again, we create first the column. For the columns, we are ranging from I equal from 0 to n base plus 1. So this means the first, the second, and the third. We are ranging from 0 to the number of stories, obviously, because we have the same number of columns as the number of stories. Remember, for the node, we had the number of stories plus 1, because for when you have 2 stories, you have 1, 2, 3 nodes. But when you have 2 stories, you have 2 columns. And we are creating the columns, okay? I mean, unfortunately, now we cannot see the full code. Let me switch like this. I did a disaster. Okay. So you can see here that we have the same representation classical of the code. We are changing here the column name and the bin name. And again, we are using the node name function we defined before to define the Boolean connection, right? So the column, the first column is connecting the node at the base, okay, the node with coordinate ij, with the columns at the floor above, right? So you have the other node, the second node is ij plus 1, okay? You can see how simple is it, right? So at this point, you have an automatic connections. And again, in this case, similar to before, we are assuming the same area, elastic modulus, inertia, and geometric transformation. But again, this can be easily changed in a parametric and proper way. Okay, at this point, you can see here, right, that we created the elastic beam column elements. So in this way, similar, we follow the beams, okay? Again, we use this function beam, is exactly the same as this, but we have a 2 in front. And we are changing a little bit the connectivity here when we are creating a beam. As you can see, we are connecting the node ij with the node i1, I plus 1, j, because we are connecting the end of the column I with the end of the column I plus 1, so the next bay, okay? And then we are copying everything. Then we can also make a parametric representation of these loads here, as you can see here, right? For instance, let's find this. I put 2 examples, we will see in a while. One is a typical lateral load representations, where you can see here, again, I use the node name function. You can see how easy it is to build a frame. Again, we use a time series linear with the value 1. We don't use a pattern for dynamic analysis similar to Tony's Berna. We use the plane 1, 1. And in this case, you can see I created a series of loads applied to the first column. In fact, I'm only iterating on j, which means the different heights. Starting, you can see from 1, not from 0, because I don't want to apply the force at the ground level or the base level. I fix I equal to 0 because, again, I want to apply these loads only on the first column. And then, as you can see on line 89, and finally on line 90, you can see I'm applying this OPS load to this node name. Again, I'm reusing this function. You can see what is the advantage to define this function that makes everything easy to move inside your structure, and I'm applying a certain force, okay? In this case is a positive force, which means positive x direction. I'm not applying any vertical or lateral direction. Then, I mean, here inside this commented part, you can see also a series of distributed load. I think it's a similar logic. If you want to apply the same load equal to minus q to all the beams, you have a similar logic, right? For EI, in a range of n base, right? Because we have 1, 2 each beam. J, we start from 1 to the n stories plus 1, because at the ground we start from 1, because at the ground level we don't have the beam, right? But if you have a beam potentially, right, you can also apply the load, and you use the OPS LA load, using in this case beam name, because we are applying to the element. You can see IJ, type, applying a beam uniform, minus Q means in the transverse direction without applying any horizontal load, okay? Then the remaining part are exactly the same. I think I didn't modify the recorder, but I think it's easy if you want to modify the recorder by yourself. And you can see it's exactly the same as you have seen before. You can print something, some information you feel is relevant. And at the end of the day, you can also use the OPS-Vis package to plot some part, plot some model, okay? And have relevant information about this, okay? Okay, so we can run this code, okay, like we have seen before. And you can see very well that it's quite easy, okay, for instance, to have some information, okay? So you can see this is your structure. I think it's clear now, the notation. we have two horizontal forces. Obviously, I show you that we have two possible loads. I will show you first the case where we have the horizontal load, right? And then I will uncomment this part to show when we have distributed load. We can have also a view about the deformed shape. Okay, obviously the amplification factor is not so big in this case, but you can see that when I'm applying these two 10 force here, you can see we have a displacement in the lateral direction of our frame, and we can plot, this is very useful, the axial force diagram. Okay, obviously you can see that we have this different sign of the axial force because we have the one part of the moment is under equilibrium by the two axial force developed on the two columns. In this case, the axial columns, due to the symmetry of the structure in the internal column, is near to zero. And we can also plot, okay, the shear force diagram and the bending moment diagram. So this is a general check, you know, guys. I'm generally asking, especially to students when they start to build frame, remember that there is a very simple check you should make on a frame, right? The total shear force at the base should be equal to the total lateral force you're applying, okay? In this case, if you keep in mind we are applying two forces of 10, right? Obviously, we should get that the sum of this shear should be equal to 20, right? Okay, this is a very basic check you must always do on your frame. Whatever is non-linear, if it's the dynamic is a little bit more complex, as Tony's Berna was showing before. In that case, you can have the inertial forces playing a game, right? So that's right, Antonio. So that's, you should consider also that there is another guy and the damping forces playing a game in the equilibrium. But if it's static, whatever is non-linear, P delta corrotational, right? This must be satisfied. Otherwise, right, there is some problem, right? And this must be satisfied also if it's a three-dimensional system, right? But you have two directions in that case, right? It's a simple equilibrium problem. Remember, equilibrium is always something we should respect. We don't know why, right? Maybe it's something from God, right? But we have to respect the equilibrium, right? Okay, anyway, I will show you that if you uncomment, okay, this part here, right? I will comment, okay, using this way, the point load, okay, lateral load. Obviously, we can create a if, okay. In this case, you can see how simple is it to transform your load into a vertical load, okay. In this case, is 5, okay. Again, I'm not taking care of the units, but I hope it's clear, right, that you should think a little bit about the units at the beginning. We can have a look about the deformed shape. I have the feeling that maybe I should amplify a little bit this deformed shape. Yeah, maybe let's amplify it, okay? Let's make 800, okay? And only to see is still equal to 0. Let's make 8,000, okay? I want to exaggerate. Okay, finally, we can see some deformation. Obviously, this depends on the load, right? Maybe the loads are too small compared to the stiffness of the structure. Okay, and you can see here, okay, that we have a typical deformed shape. And again, you can appreciate the axial force and the shear force, okay, and the bending moment diagram, okay? Again, also regarding the axial force, if you apply a certain distributed load or vertical force, again, the summation of the axial force at the base of each column, okay, should be equal to the total force you're applying, okay? Again, it's the same concept of equilibrium. So that's always simple checks you should do on your model, whatever is the complexity. Okay, at this point, I think you are able to build whatever frame, okay? Let's see. In China, okay, it's common to live in, I don't know, 10 stories building, right? They are quite high. And five bays, okay? If you click like this, you will see, I think I have to wait a little bit more for the, especially for the plot part. So you can see very easy, we have again a very complex frame, right? You want to generate another frame, you can generate, right? You want to make bigger, smaller, you can change. Obviously here we have some assumption on this part, right? But you can, for instance, make a list, right? So if you want to change the span, okay, we can try to do it now real time together, right? Is very easy, right? Let's make a list. We have 1, 2, 3, 4, 5. the horizontal direction is the L2, right? So we have simply to change L2. Let's see if I'm doing a disaster now. 0, 3, let's make 8. Let's reduce this to 4. I'm lazy. 0, 3, 8, 12, 15, okay? So that's the location of this. And instead of writing, okay, L2 by J, we have to write L2, if everything is okay, if I'm not doing a disaster, L3, no, I made a disaster, I think, because L2 is the height, right? Okay, anyway, so you have to define a list, okay, and you can recall this list here, okay, maybe if you need, I can do during the break. Now it's a little bit complex to change real time. Okay, anyway, I think it's easy, right? You want to make a building in a different way, right? You can see here, for instance, we want to make a similar building, but with 5 stories and so on, we can change. You want to apply also the same building at the same time. You can see horizontal forces and vertical forces, okay? We can again apply both together. Obviously, you can have a switch to make this automatic, okay? And you can see, I mean, in this case, the horizontal forces play a little bit more, okay? You can see from the deformed shape, right? The deformed shape with this amplification factor is quite funny. Okay, now that we have a parametric model, we want, for instance, to optimize this. Okay, this morning with Tony Berna, you have seen how to use the eigenvalue function, right? Yes. Yeah, it's difficult to self-hear if it's working or not, you know. No, but this is for the audience online, especially, right? Okay, so let's say you have this frame, okay? Obviously, in this frame, I didn't put any mass, okay? I will put now some mass to certain elements, in particular to the beam, we will put some distributed mass. Okay, according to the lecture you had with Tony Berna this morning, you learned that you can calculate the fundamental period, okay? So you can make an eigenvalue analysis, you can use OPS EIG, and with this eigenvalue analysis, then you can evaluate a certain period, okay? Now, I would like to ask you a question, okay? That's a typical question. Maybe you will spend 1 week to solve normally, but I will show you how easy it is if you have a parametric model. Can you let me know if you have a structure like this? What is the value of the cross section, okay? B and H, okay? Let's say it's a rectangular cross section. The value of the cross section of the column, we are assuming they're all the same, giving you a certain first period, okay? We will try to solve this problem, okay? You will see that it's super easy. I mean, this is an example, you know, I just developed for this class, but obviously this can be extended, you know, to whatever interest you have. Okay, let's close these examples and let's move to the example number, I'm fighting with my computer, with the example, okay, 2.1, okay? Frame elastic, okay? So here, let's open this example. You will see that I have something very similar to what I've shown you before, okay? We have, again, the number of stories. Let me zoom a little bit, especially for the, I don't think for the audience online, but for the audience in the classroom. So you can see we have a certain function, okay? This function, we have BC, HC, and BB and HP. You can see we have this code, okay, again, representing the similar stuff that we've seen before. We have number of stories and number of bays. You can see here that the main difference is that in this case, I'm calculating the properties of the columns. The C indicates columns and B indicates the nodes beams, similar to, I mean, I'm only changing B and C, okay, with A and B. And you can see I'm creating a function. Inside Python, to create a function, you need the def, frame period, the input variables represented basically as a list, and then with a certain indentation, you put everything. So once you have a parametric model, you can simply create a function, okay, put everything inside the function. That's something generally I'm doing. Comment, as you can see, line 29, 30, 32, and 33, the variables, the input variables you are considering, and you transform your structure into a parametric function. At this point, once you have a parametric function, I can show you, everything is super easy, okay? So obviously here you have, okay, something very similar. The only difference here is that you can see I add a certain value of the mass, okay, to calculate the eigenvalue to the beam elements, okay? So the masses are represented as distributed loads inside the beam. And you can see here that we are calculating, according to the procedure by Tony's Berna, the eigenvalues here. And you can see at this point, we have omega, f, and t. And you can see here we have the different frequency. You can control this by a variable called number of modes. And you are storing, okay, I'm storing here everything on line 106, but I'm not using inside a dictionary, but that's only, I mean, as a game. You can plot the mode shape exactly using the package OPSV, and we are returning the period, okay? So once we have a representation, a parametric representation like this, we can play with our structure, okay? So you can see here, first I'm importing everything. So I have this function. Once you have this function, everything is easy, right? So let's say I want to know the period. Okay, obviously in this case, we have 4 stories and 4 bays. We can change this if we want, but let's say we want to frame, you can see here, we want to calculate the frame period of a structure. You can see with a base column of 0.5, a height of the column of 0.5, okay? Let me fix this. And we want to have a base of the beam of 0.5, okay, for instance, and 0.7, right, of the height of the beam. You can see here, I have very fast the first 4 modes, right? The first 4 periods. The first period of this structure is 0.46 seconds, okay? The second period of this structure is 0.15, 0.09, and 0.07, right? Obviously, if I want to plot these modes, I stop the plot of the mode somewhere here. Where is this? If plot, let's find this variable. Plot mode shape, right? Where is this plot mode shape? Here, so it's false if we put true, right? And I am redefining this function, okay? Let's only show you, very easy. Tac. I'm recalling this. Additionally, I'm obtaining the typical modes of a structure like this, okay? What is called the dancing frame, right? I like to think a frame dancing, right? Do you like to dance? Like frames, yeah. You know, we have to make a function similar to sub 2000 with that music, right? The tum, tum, tum. So this makes more active the structure, right? But the animation by Tony's Berna were very impressive, I have to say. Anyway, you can see here that we have the period. Obviously, we can change it. So let's see, you can check if your model makes sense, okay? This is what we call the parametric investigation, right? So if I change my columns, okay, to be 1, 1, what is your expectation? My expectation is obviously, okay, also the mode shapes are changing, obviously. I made the columns quite big. My expectation is that the structure is much, much stiffer, right? And then the period is going down. So you can see the model makes sense. Before with a column 0.5, 0.5, I had a period of 0.46, increasing the column to be 1, 1, okay? 1 meter by 1 meter is quite massive, okay? We had the first period of 0.25, okay? So this is very important because you can control if there is a physical meaning, right, in your model. Remember, when you change the parameters, you should find something you're expecting. If you don't find something you're expecting, it's not meaning that the model is wrong, but maybe it's meaning that you're not under. So one possible solution in 99% of the cases is that the model is wrong. But another case is that you are not understanding the problem, okay? So this is sending you in 2 possible directions, right? Yeah, when I was a PhD, I remember, you know, my supervisor told me if you cannot understand the model, means the model makes no sense. But I think that's a very important way to see this, right? So if you cannot understand the model, is a useless model. Okay, that's relatively simple, okay? I'm not saying that all the models are so simple, but generally use this approach is very important by changing the variables and check if you have some sense. And also to develop a sensitivity to the model, okay? If you change a little bit the parameters, okay, and you notice that the answer is similar, there is no sense to get crazy, okay, to get more information on your problem, right? This is very important in general. Okay, reach this point, basically what we can do. Okay, what I would like to try to do with you is to solve the following problem, okay? If I want to have, is an inverse problem, okay? So I have this structure. I can control, as you can see here, the cross-section of the column. I want to change the cross-section of the column to have a certain first period or fundamental period. If you have to approach to this problem, probably you need a lot of time. Normally, right? I can imagine a normal student starting to try to click, right? And if you have one variable, it's easy, right? If you have 3, 4 variables, right, you can click forever, right, in your computer, right? By changing this and that number, right, until you will find the right frequency, right? So I remember again, when I was PhD, I had a lovely colleague, you know, he was doing Monte Carlo analysis by hand. He was sampling, okay, the input parameters. At the time, I think he was using Seismostruct. I'm discussing about something 15 years ago. He was doing like 500 simulations, you know, in Seismostruct by changing the analysis one by hand. I think it's possible. I'm not saying it's impossible, okay? But you start to program, you know, I would say something that it sounds strange, but you will start to love programming if you are lazy. If you are not lazy, you will do by hand. If you're lazy, I like to program because I'm a lazy person, honestly, right? So people are thinking I'm very active, but I'm very lazy in reality. Okay, how to approach to this problem? Okay, if we have one variable, the easy solution is what you can see from line 124 to 125. It is what is called a parametric investigation aimed at finding the proper value, okay? So let's say we want only to change in our model, okay? We want only to change in our model the base of the column, okay? One of the dimension of the column. Let me remove 1 second the plot of the mode shape, or we will be a little bit crazy. And let's stop the code in line 137, okay? So you can see with this simple approach, okay, where I stopped. Sorry. Okay, here. Yes, okay, you can see if I use the code from line 120 to 135, I can make a parametric investigation of my model. This is very useful, again, to check if it makes sense, right? Before I start by hand, right, I use the function, right? I show you if I change the column size, I found some sense. But here what I'm doing, I'm creating a vector, okay, with the NumPy package, starting from 0, 1 to 1 with 10 steps, okay? And this is basically the value of the base of the column I would like to investigate, okay? Then I'm creating an empty list containing the period, okay, that's the output of my model. And then you can see in a very simple cycle, I'm iterating from using the index I, okay, the variable I, inside this NumPy array, okay? So this means that this I, you can see, we can directly plot it, is print I, is giving you as an output, you can see the different values from 0, 1 to 1, okay? Don't look about the small numbers, it's only numerical stuff inside the conversion between binary to normal digits, but it's not important. In any case, it's not propagating in our problem. And you can see at line 125, I'm evaluating my function, the function I defined before, where if you remember, the first input is the BC, so the base of the column, and I'm fixing the height of the column to be 0.5, and the cross-section of the beams to be 0.5, 0.5. Obviously, I can change this to whatever I want, right? I have only to move this I in another position and fix the 4 variables. And obviously, if you want to check other variables, you can simply change the function by modifying the inputs and having different inputs. And then for each of these I, so this means these numbers here, these 10 numbers here, I am populating the list T, okay, by appending at each iteration the first value of the output, which is TV. Please keep in mind that TV is giving you the first 4 periods at the moment, right? So I want to take only the first periods, therefore you can see that I took only the first index as represented inside the square brackets with the number 0, remembering that listing inside Python. And then I'm creating a very lovely figure, very simple figure, right? Honestly, the scale of the figure is not so nice, so you can make it better, right? So you can make 5, 4, you know. I'm always fighting with my students about the quality of figures, but this is a personal war. You can see here that you have the base, okay, of the column as a function of the period. Obviously, in this case, if you want to have a structure with a period 0, 6, right, you can read on this diagram, right, for a structure with 4 spans, 4 base, and a high, one sides of the column 0, 5, and beam 0, 5 by 0, 5, right, you need a value of the sides of the column of around 0, I would like to say 45, right? Something like this. Similar, if you want a period of 0.5, right? You need 1 meter, okay? That's a very simple way to optimize your problem and try to understand it. Obviously, that's a slight extension of the end approach, right? Like my colleague when he was doing the Monte Carlo analysis by hand, right? So we can, if you have 2 variables, I think you can extend the concept as you can see here, right? In the part I highlighted from line 137 until 169. Here, it's the simple extension of this concept in 2 variables, right? So we want to investigate the variability of the period, okay, by changing, okay, the base and height of the column, right? You can see is simple an extension. We create a grid, right? We made a mesh grid, okay, of these 2 variables. And then we created a T matrix, in this case, containing all 0 elements, and then we are populating by performing an analysis in 2 index, okay, you can see here where we are iterating into index, and we are plotting, okay, we are plotting the contour plot. Okay, let's plot it. So again, let's make maybe this plot a little bit smaller so you can see it better. And if I run this lovely code, you can see I'm obtaining the 2-dimensional extension of the case I just showed you before, right? So here, you will see that you will have the fundamental period, okay? This is the color bar is representing the different periods as a function of the height of the column and the base of the column. Obviously, again, we can make a check of our model, increasing the height of the column, the period is decreasing, right? You can see we are moving from light to darker color. And similarly, increasing the base of the column, we are decreasing the period. Again, we are moving. And obviously, when we are moving the both variables, okay, we are moving. Now, I mean, obviously, you can use this again, and you can find that if you want, for instance, a period of 0.6, there are multiple solutions, right? In this case here, right? So we can find multiple solutions, and all the points here, you can see on this line, are satisfying the requirements of 0.6. Okay, another way you can approach to this, okay, after you know the problem, is to put this as an optimization problem, okay? So if you want to optimize it, in this case, we can start directly by the definition, okay, of a target, okay, on line 165. For instance, let's say I want a period of 0.5. And in this case, the general way we are approaching to the optimization problem is by the definition of an objective function or goal function. A goal function is basically a function representing a certain error between the value you want to obtain and the value provided by a model, okay, or the output of some functional model. So in this case, you can see that the objective function is entering with the 2 parameters, okay, BC and HC. With this BC and HC, I'm calculating T. T, again, is a vector containing the first 4 periods. And you can see here that we can calculate the error defined as the absolute difference, okay? So the absolute difference between the predicted on line 171 T0, the predicted value of the period, T0 means the first period, minus the T target, okay? So this function is basically returning 0, okay, if the periods are exactly the same. It's returning a larger number if the predicted period is larger than the target period. Obviously, the absolute value makes sure that is a minimization problem, so the minimum of this problem, if it's existing, is located at 0, 1. Okay, in this case, I use in this code the optimization package by the SciPy package. So we start from an initial guess, okay, of 0,2, 0,2. Okay, we say the cross section is 0,2 by 0,2. We define some bounds, so we say that the maximum value of the cross section is between 0,1 to 1, 0,1 to 1, and we write in this way the optimization problem, right? So we say OPT dot minimize, then we give the objective function, so it's a minimization problem written like this. We give the initial guess and we give the bound, so we say that these two variables can be between 0, 1 and 1, okay? Reach this point, okay, we have the optimal values of BC and HC, okay? If you click from this variable results.x, you will find basically the best values. By substituting these two values inside the function again frame period, we can see the optimized value, okay? And finally, I mean, we can plot with a similar approach as we have seen before, okay, the output, okay? We can run this code again together. Maybe let me make this smaller again, 5, 3. So in this code, this part here of the code, okay, is giving you the best solution, okay? You can see here, the best solution is a solution with a cross-section 0,6 by 0,6, where you can see the resulting period is exactly 0,5. So let's remove this numerical unexisting stuff, right? And you can see also on this plot here that, I mean, it's difficult to see because of the scale of the color bar, but the optimum is here and is corresponding to a minimum of 0,5, okay? So if you can write in this way, basically you can optimize whatever model, right? So that's a typical way. For instance, when you have the period, generally you're not changing the cross-section, but you can change the elastic modulus, right? That's what we call model update. So if you change on the initial function the elastic modulus, then you can easily tune your model. Then you can also optimize, for instance, by difference with the modal frequencies. The last example I would like to show you is a truss, okay? This is a simple truss I took from an example on Opensees Spy. So web page. So I mean, this is to let you know that you can have whatever problem. Let me maybe find Opensees Spy. So I took this example. If you go to the example, structural, nonlinear truss analysis, okay? I copy paste basically this example inside the next code, okay? I mean, to let you know that you can take whatever model, transform into a function, have input, and then optimize for a certain variables. So I took this with very slight modifications, but it's exactly this problem here. Let me open it, truss opt.py, where we are here. Okay, in this case, my goal, okay, is a nonlinear truss, similar to what you have seen yesterday with Fabio Di Trapani. So this means you have the truss element represented with this uniaxial hardening material. The parameters in this case are E, S, Y, and alpha. So I use a different parametrization in this case of the problem. Instead of directly defining the variables, okay, the E, alpha, and SY, I define these variables multiplied by a certain coefficient correcting it. In this way, it's easy because this number is equal to 1 if you have the original values, is below 1 if it's if the parameter is smaller, and larger than 1 if the parameter is bigger. And obviously you can bound these parameters to 0 if you physically know that for some constraint this must be a positive or negative value, so you cannot switch from positive to negative. Okay, in this case here, okay, we have exactly the same. I don't want to spend too much time on the model, but we can approach, okay, again, by using the first part, first using a similar approach. Let me comment, okay, because then I will show you in the final part how to also use a genetic algorithm, but you can see the logic is exactly the same. First, okay, if you have this model, you can calculate the displacements, okay? For instance, let's say we want, by changing the yielding value of the material, okay? You want to change the yielding value of the material, denoted here as theta sy, so we are changing the yielding value of the material, to have a certain value of the displacement, for instance, 2. Again, we first start from this function. Please remember that the first modifier is the modifier of the elastic modulus. The second one is the modifier of the yielding value, and the third one is the hardening coefficient. So I fixed one, the first and the third, which means the elastic modulus and the hardening coefficients, and I change the theta sy, okay? So we write exactly as the previous case from line 113 to 116, the objective function, where we are basically comparing the displacement obtained by the model, okay? The maximum displacement at the end of a certain force value, is not important what is the value, but in this case with the target. We start with an initial guess, you can see here in this case of 1. We are thinking that the model, the value should be less, okay, of this. So that's the reason, because we have this bound from 0, 1 to 1. But I mean, we can change this bound to 0, 1 to 2. I mean, if we feel a little bit constrained, that's if we don't know. And you can see everything is exactly the same, right? So at this point, let me run the code, okay? You will see, okay, at each of the iteration, okay, it's replotting, I mean, because I didn't block the plot, so it's plotting the constitutive load, the force displacement plus the structure, so you can see the different iteration, and you can see that it's searching the best value of the coefficient in order to provide a solution, okay? So you can see, I think the algorithm is basically converging to something around 0.68. You can see the first and third coefficients are not changed. And I mean, at the end of the day, we will find that the optimal value of Sy is 0.68 with a resulting displacement of 2, exactly, to I don't know what, again, because I'm not discussing about units in this case, but please keep in mind you should take. And you can see exactly, you have a constitutive law with a certain elastic stiffness, a certain hardening, again, the force displacement of this structure, you have a force applied here, exactly giving you 2, right? Obviously, if I'm increasing the target, displacement, right, to 2.5, right? Let's rerun again this example. Remember, before we obtained something like 0.68, right? Obviously, I'm expecting that the yielding stress should go down, right? Because to have more displacement, right, you should have the yielding before, right? Because then you move on the hardening side. And as you can see, in this case, now we are almost reaching the convergence of the model. We are finding 0.52, okay? Obviously, you can approach to multiple variables, okay? There is, you can tune whatever you want. You can tune whatever constitutive law inside Opensees using this approach. You can have a uniaxial material and then optimize it. And finally, for more complex problem, because obviously the approach I just show you is limited, okay, in some sense, okay? You can also implement a genetic algorithm or whatever heuristic, meta-heuristic approach. You can see the last part of the code, I commented the previous one, where you are using the genetic algorithm. In this case, I will show you an example with this very nice package called PyMu. Inside PyMu, you have several algorithms like genetic algorithm, particle swarm, and many more, also for multi-objective optimization. I think I lost the connection. Let me stop my VPN. What's going on? I don't know what's going on. Why is it not working? Okay. Work. Okay. Okay, and to complete, I mean, you can see here, I mean, I will not spend so much time, but I mean, you have an example here, but you can adapt to whatever example. So again, I would like to transfer you the logic, right? Define the input variables, right? Try to make this model working with your input variables, put everything inside a function. And once you have a function, here you can plug inside PyMove, but there are PyGAD, there are many packages I use for this optimization. You can see, write your specific code. Again, you can recognize your function where it's used. This max displacement is used here, right? And this is again is your goal function, is exactly the same as before. And in this case, I'm using a population size of 5 and 10 generations. Okay, that's not important. If I'm running it, okay, you can see that, okay, we finished the first generation with 5 kids. We have the second generation, 15 kids, 20 kids, 25. The kids are lies. And yeah, the kids. And then you can see we reached 0.69. Okay, in this case, with these kids, Tony's Bernard disagree with my vocabulary, but he's a native speaker. Yeah, so you can see that you will find 0.69, okay, and the displacement obviously with a meta-heuristic algorithm and with this discretization is not so good. We obtain, it's not so good, I mean, we obtain 1.98, you obtain something very near to what we have seen before. Okay, so this was a very, I mean, rapid introduction about this, but I hope that the example you have will let you build, right? You can take whatever of the examples you have from Fabio or from Tony, and you can change it to make it optimized to your problem. This is a typical problem when you have experimental data, for instance, right? You have a model, you have experimental data, so you want to reproduce a certain, you define your goal function, and you can tune the parameter in order to reproduce it. Please keep in mind, obviously, to a solutions with certain set of parameter is not the right solution. So sometimes this is called tune parameters, right? So you have always to think if the parameter makes sense then in a physical space. What I want to say, if you have a numerical model and you apply this approach, right, and you find an elastic modulus of steel, right, of 100 gigapascal, right, this makes no physical sense, right? Okay, so always keep in mind that the model should work on a physical base. Otherwise, you move to fully data-driven, right? But I don't know if you need finite element analysis, right? You can move to machine learning, right? Skip the finite element part, right? Directly move to full data-driven, right? And you skip the model, right? So what I want to say, this is a very powerful technique, right? You can always tune your model, but think about if the input parameters make sense. With that, I think it's time for Chufan, right?
Yeah.
And for questions, I don't know if you have questions online or in on site. Otherwise, Chufan time, right? Great. Great.
Oh, wait.
But they are hearing me online, right? I hope they didn't lose off the. Yes, lunchtime. Great. Thomas, have a nice lunch. See you later.